an independent editorial analysis of Japan's defense posture and security policy.
The arithmetic of modern naval warfare has become increasingly unfavorable for defenders relying solely on kinetic interception. The proliferation of low-cost unmanned aerial systems and loitering munitions has created a distinct cost exchange disparity. In this environment, the defensive ordnance is frequently orders of magnitude more expensive than the incoming threat. This financial and logistical asymmetry provides the necessary analytical lens through which to view the recent integration of a 100 kilowatt class high-energy laser on the test ship JS Asuka. Rather than viewing this development as a singular technological breakthrough, it is more accurate to assess it as a systemic response to saturation tactics that threaten to deplete the magazines of the Maritime Self-Defense Force surface combatants long before a high-intensity engagement concludes. The strategic imperative driving this program is not merely the acquisition of a new weapon type. It is the restoration of sustainability in maritime air defense. From a systems engineering perspective, the transition of directed energy weapons from experimental laboratories to a sea-based platform like the Asuka marks a shift from verifying physics to verifying utility. The core operational value proposition of the high-energy laser lies in its potential to function as a deep magazine capability. Unlike the vertical launch systems that define the current lethality of the Kongo, Otago, and Maya class destroyers, a laser system does not suffer from a finite ammunition count in the traditional sense. As long as the platform can generate sufficient electrical power and manage the immense thermal loads produced during lacing, the weapon remains operational. This theoretical inexhaustibility addresses the logistical nightmare of reloading vertical launch cells at sea, a capability that remains operationally difficult and strategically vulnerable. The recent trials suggest that the Acquisition, Technology, and Logistics Agency is prioritizing the interception of subsonic, low-altitude threats. This would allow the fleet to reserve high-value interceptors like the Standard Missile-6 or the evolved Sea Sparrow missile for more complex supersonic or ballistic targets. However, the integration of a 100 kilowatt laser introduces significant architectural constraints that extend beyond the weapon itself. The primary challenge for the Maritime Self-Defense Force is the size, weight, and power requirements, commonly referred to as SWAP. Generating a lethal beam of this magnitude requires a substantial power source, and perhaps more critically, an extensive cooling system to dissipate the waste heat. This creates a platform dependency that limits the retrofit potential for older hull designs. While the Asuka serves as a testbed, the operational deployment will likely require platforms designed with significant power generation margins, such as the upgraded Mogami-class frigates or the future Aegis system-equipped vessels. This highlights a critical trade-off in fleet design. Future hulls must sacrifice internal volume and displacement to accommodate the capacitors and chillers required for directed energy, effectively altering the density of combat systems per ton of displacement. Furthermore, the environmental realities of the Indo-Pacific theater impose strict physical limits on the efficacy of directed energy systems. The operational environment around the Japanese archipelago is characterized by high humidity, frequent precipitation, and heavy maritime aerosol concentrations. These atmospheric conditions contribute to thermal blooming and scattering, factors which can drastically reduce the coherence and range of the laser beam. Unlike a radar-guided projectile, which remains effective in adverse weather, a laser system suffers performance degradation proportional to the opacity of the atmosphere. This physical inevitability suggests that the high-energy laser will not replace kinetic close-in weapon systems like the Phalanx or the CRAM. Instead, it will likely operate as a fair weather force multiplier. The doctrine, therefore, must evolve to manage a hybrid defense architecture. Commanders must dynamically select between kinetic and non-kinetic effectors based on real-time meteorological data, adding a layer of complexity to the decision-making cycle in the Combat Information Center. The industrial implications of this program reflect a broader effort to cultivate a domestic supply chain, one capable of supporting advanced optical and power electronics. The involvement of major heavy industry conglomerates in developing the beam director and power supply indicates a deliberate policy, and a policy to retain intellectual property and technical competency within the national defense industrial base. This contrasts with the off-the-shelf procurement of foreign systems. It suggests that the Ministry of Defense views directed energy as a foundational technology for long-term sovereignty rather than a gap-filler solution. The budgetary allocation for research and development in this sector, which has seen a consistent upward trajectory in the fiscal year 2026 requests, reinforces this assessment. It appears to be a multi-decade capitalization strategy. The goal seems to be the gradual scaling of power output, potentially aiming for the 300 kilowatt threshold required to engage cruise missiles in the terminal phase, thereby progressively expanding the defensive envelope of the fleet. See, technological interoperability with the United States Navy also plays a silent but substantial role in this developmental trajectory. As the United States advances its own directed energy programs, such as the Helios system, there is a convergence in the standards for power distribution and fire control interfaces. A shared architectural standard allows for greater integration within the alliance framework, potentially allowing Japanese and American assets to coordinate target handoffs between kinetic and non-kinetic shooters. However, this interoperability brings its own set of dependencies, particularly regarding the software algorithms required for beam control and adaptive optics. The challenge for Japanese planners is to maintain a degree of strategic autonomy in system design, while ensuring that their platforms can seamlessly plug into the broader Allied integrated air and missile defense network. From a cost management standpoint, the successful deployment of laser systems offers a potential mechanism to flatten the cost curve of air defense. If a drone costing $5,000 US can be neutralized by a laser burst costing a few hundred yen in fuel, the economic leverage shifts back to the defender. This reversal of the cost-exchange ratio is critical for Japan, given the fiscal constraints of an aging society and the sheer volume of threats posed by regional competitors. However, this economic benefit is prospective. It relies heavily on the reliability of the system. If the laser requires frequent, specialized maintenance or has a low mean time between failures, the life cycle costs could exceed those of the munitions it is meant to save. The rigorous testing on the Asuka is likely focused as much on reliability and maintainability as it is on beam quality. As a weapon that cannot survive the corrosive maritime environment offers no strategic value, regardless of its theoretical efficiency. Ultimately, the trajectory of Japan's directed energy program signifies a recognition that the traditional methods of fleet defense are approaching a point of diminishing returns. The introduction of high-energy lasers represents a transition from a strictly resource-limited defensive paradigm to one constrained by power generation and atmospheric physics. This shift necessitates a fundamental reevaluation of ship design, logistics, and engagement authority. The forthcoming years will likely see a period of operational experimentation where the limitations of the technology are as instructive as its successes. The strategic value of the laser lies not in its ability to render missiles obsolete, but in its ability to preserve the high-end kinetic interceptors for the engagements that determine the survival of the fleet. This capability preservation is the central pillar of the modern denial strategy. Acknowledging that in a protracted conflict, the victor is often the side that runs out of ammunition last.